Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Dianna Dini.
And this is Fred Shankberg. Hey, Dianna.
Hi, Fred. I have a question for you today.
Okay.
If you don't mind me asking you a question.
No worries.
It's about reliability prediction standards.
Oh, now I do care. Yeah, that's a bad question.
Well, when I first started out as a reliability engineer, I had some great mentors, and they gave me a bunch of books. They were published books they pulled off the shelf, and they said, here's some reliability prediction standards that you can use as a baseline for your engineering.
Mm-hmm.
But that was a few years ago. Couple dozen years ago.
Mm-hmm.
So, now I was re-looking up reliability prediction standards, and they seem to be, I don't know if they are out of date. Some companies stopped updating them, and then other companies picked them up and are continuing to publish them. So is it depend on the industry, like the electronic chips industry? Are they still publishing these standards, or are they relying on the vendors to do that? And what about just the speed of innovation, and everything's changing so fast? Are these standards still applicable? So I have some experiences with these standards, but I really wanted to ask you about it.
Well, there's a lot in that question.
Well, what's been your experience with standards? Have you used it in your reliability designs?
That's a complicated question. First off, let me make it clear. Please don't use standards. And what we mean by reliability prediction standards is best characterized by Mill Handbook 217. It's a listing of component types like capacitors, multi-layer ceramic capacitors. And it says the base failure rate is something. And then it has a bunch of factors you can apply to it. And depending on your particular circumstance. And I know some of the people that work in Telcordia to put it together their database. And so back when Ma Bell, basically Bell Telephone Company, pretty much owned everything, including the phone in your house, and all the switchboards and all the other stuff and all the transponders and every other component. And they would do failure analysis on their own equipment to the component level. They actually had pretty decent data of their own systems. But and HP did this back in this late 60s, early 70s, when they were only primarily doing test and measurement equipment, they would do failure analysis to the component level. And they created an internal database just for their own products because it was their components, their designs, their customers, and it actually gave them a pretty decent picture of, the components from in this circumstance don't do as well as components in a different circumstance and so on. And so they got pretty good data on some of this stuff. Well, Mill Handbook 217 was based on military equipment. And it had, is it on an aircraft? Is it on a tank? Is it, is it in space? You had all these different environments. And it was publicly available. It was a military document that was in public domain. So it got widely adopted, even after it got canceled. And now I'm drawing a blank. It's been 20 years, 25 years since it's been stopped being revised. The problem with the standards is, I think you mentioned it in part of the question, is that they're out of date because they're not being updated. And there's many, many factors for that. One is companies that make capacitors are competing with other vendors, but the standards are lumping them all together. So they don't want you to use the standards because that's kind of the lowest common denominator, and it's being held back by other people that are worse than them, and they're not better than them. So other companies came along and said, well, we'll check with all the vendors and create a vendor-specific parts list, and you pay a huge fee to have access to this. And other companies didn't share because now they considered it trade secret, and others, the lawyers got involved and says, no, you can't talk about how often our parts fail. Besides, we don't even know because our customers don't tell us. And my favorite take on this was by Patrick O'Connor, who wrote the reliability, practical reliability, the handbook in reliability engineering. And in a presentation, somebody asked him one time what he thought about predictions. And he said, when he was in the Air Force, early, way back when, he was a radio repair technician and had all these radios that needed repair in the military system. And they'd take parts out, put parts in and test it and get it back in service and ship it back out. But they had to fill out a form that what component failed and how old was this piece of equipment. It was kind of the data collection you would think would be really useful for estimating time to failure or failure rates for components. And he said, nobody checked us. And we were doing shotgun repairs because we had to get it done real quick. So we'd pull out 20 parts and put in 20 parts and hope it worked, kind of thing. And unless something was obviously broken, we didn't really know why it failed. We didn't have time to sort that out. And usually we just kind of randomly filled out these forms so that it looked like it was spread out a bunch. He goes, and he said, where I sit now is I know that was being used to figure out how to do these parts count prediction standards. He said, I didn't know. Nobody told me what this was for or how it was used or whatever. And nobody checked it. Nobody cared. It was kind of in the way of us doing what we were told is important. So
just a piece of paperwork you got to get done with before you can move on to the next part.
That's right. And it was garbage in, garbage out was his opinion. And then years later, I found a study. A friend of mine I don't know if he still is, but it was a professor in England, and had a bunch of his grad students take an identical circuit board that they happened to have about 5 years of field data on. They had actually really good time to failure data and failure analysis on, down to the component. And I mean, it's a great small data set. And it was a single circuit board, but it was installed in a couple thousand places and they had really good data on it. And so what he did is he asked, one team of students to do the French prediction technique, and the other had the British standard, and the other had the Milner Handbook 217, and somebody else had the Japanese one, somebody else had the Chinese one. And Telcordia and all the different variations, they had, 8 or 9 in this study. And they all came up with very different predictions for the exact same circuit board. Some off by a negative 200% to a plus 600%.
Oh, wow.
So, and none of them were even close to what the actual was. And then if you go into most standards, I don't read Japanese or French, but the standards I can read, they almost always say in the introduction or early part of the document that this is not a reflection of field reliability. This is not what it's for. And when the very first time I ran into these prediction things, I was at Hewlett Packard, and one of the divisions asked us to do it for them because it was a condition of sale. This company would not buy their tape drives unless they had a parts count prediction. And the division said, we don't do that because it's senseless, kind of thing. Can you do it? Because we think you mentioned that you have that software that can, make it pretty easy. Could you just run it for me? And so I started filling it out and going down the bill of materials. And I thought, this is crazy. So I went down and talked to Dick Moss. And he said, yeah, it used to be really useful, but there's not really anymore. But it does drive the right behavior. in the design teams. He says, if you have fewer parts, you have fewer solder joints, you have fewer bits and bobs and pieces and suppliers that can get things wrong.
Mm-hmm.
And so fewer parts typically means more or higher reliability. And also a big part of many of the prediction standards is temperature. So if you keep it cooler, if the internal temperature rise is minimized, it generally means it's more reliable. And both of those things are generically true in most circumstances. I mean, you can get crazy with no parts and then it won't be reliable at all. And he said, all right, so it's kind of a necessary evil. He says, for all practical purposes, never use it to represent how reliable your product is, because that's not what it's for, and it's not what it's good for. But unfortunately, in industry, it's become accepted as how to compare one vendor to, one system to another, or, put it on your data sheet and doing all these other things. So it's being misused a lot. And so it's tainted my view towards these things for a long, long time. But if it's condition of sale, and some industries require it, their procurement guys have had it etched in stone in their contracts for decades, and they won't buy from you unless you run this analysis. And it's like, it's a sad story in my mind, because we've lost its initial glimmer of hope when it was your parts, your designs, your customers, and you did good failure analysis. But many of those things broke down.
So even within the companies that you've worked with, there really wasn't internal standards for reliability of parts either. I mean, let alone the publicly available published ones.
Right.
But companies weren't doing them either.
Well, HP, once they got into more consumer products and repairs needed to be faster and less expensive and easier to do, and supporting their equipment, they would replace entire boards and not do the failure analysis. So which of the 200 components on there failed? They didn't bother to find out, because the service groups were restore the equipment to service, get it running again. And detailing out the component that failed just fell by the wayside. And there wasn't the continued effort to understand and maintain the model. And so eventually that internal model faded away as being useful as new technologies came on, new manufacturing techniques came into play, and as it just became less and less and less relevant. But it's amazing to me that, I got a question early last week that was, are there any free or inexpensive parts count prediction databases available? And I was like, oh, don't use it. Please don't use it.
Not really.
Yeah. There are free ones available, but it's obsolete, been obsolete for 25 years. And there's others that, you can find that aren't terribly expensive, but they are exceedingly not useful and misunderstood and misused.
And especially you get so particular with a use case of a product, for a particular design, that the published standards, if they're still testing, they're testing to something probably different.
Well, the standards bodies typically don't test the components. They're just gathering what's available in like the military has a couple different sites and programs that they report, this capacitor failed, or this, these under these circumstances and conditions. And then there's folks that will gather that kind of data and aggregate it so that it would be able to do a failure rate. But the last time I talked to this guy that was working at Telcordia, he says that more and more companies are just not providing the information. One, because they're not doing the failure analysis, and two, because their lawyers say don't share this stuff because a vendor will sue us for saying their parts failed.
Yeah. Mm-hmm.
And so the ability to get the data is eroding, which degrades the ability of these databases to be accurate. And then what Telcordia does is, if back when they were only doing it for their equipment, it really doesn't apply to airplanes. Airplanes are usually not strung up to the telephone network.
Right. That gets into the use case.
Right.
Yeah.
But it would still be used. And the mill standard 217 has been out of date and not updated for at least 20 plus years, but you still see it in contract as required. And the worst part of it is that some vendors don't bother to figure out how reliable their own components are, and they just use the published 217 failure rate. Or they fudge it a little bit saying, yeah, we think we're a little better than that now. But they have no data. Their customers don't tell them how their components are used or when they fail.
Well, and like you mentioned earlier, sometimes that's a sales case, right? That, hey, our component is really reliable. You want to use ours versus a competitor's product.
Right. But they may or may not have any evidence one way or the other. And I've run into this more in small modules and subsystems. They'll just do the 217 or Telcordia or whatever prediction thing and say that's our reliability. Okay. None of that is, one, supposed to reflect your field reliability, and two, it's most likely wrong, but we don't know which way. As opposed to working with another vendor that has a subsystem saying, we know it's the optocoupler, and here's the Weibull distribution that we've studied that says here's the life-limiting elements or time to failure distribution for what we think is the weakest component in our system. It could be a little bit worse because all these other components contribute, but that's how we approached it. And others say, we're doing life testing and doing other stuff. But it is tough to find really good time to failure data at the component level. And there's professionals and whole organizations are trying to do that. But even if you go from vendor to vendor to vendor, you find wildly different claims and trade secret bandages all over the top of, we can't tell you how we got that number. Like, okay, never mind.
Well, that's very interesting to learn about the whole history of all these standards too.
Oh, now you make me sound old.
What? No, you're just learned.
I had a lot of experience with it. Yeah. No, it's one of those things, and you see it in some industries, it's required. So, I mean, part of my overall frustration with it goes back to MTBF, because most of these prediction things spit out, and the software packages that implement these things give you an MTBF number, an MTTF number. And I'm like, really? You got a fan in there and you're saying that has a constant failure rate for all time? Really? That's not true. But we have to put a number in it that makes it easy to add. And it was one of the technical things I ran into early on, is that the prediction standards almost always use fit rates or I think that's redundant. Failures in time. Yeah, no, fit rate. Rate sounds good on that. I hate our language.
I think you're right. You're right on the money. I think we're good.
But if I had a Weibull distribution or the appropriate distribution for every component and every failure mechanism within every component, it would be an exceedingly valuable database. And I talked to some of the software people that design these things. And one of them was was a lead designer for the mathematics of setting up something like RELX, which was a parts comp prediction. It's now bought by somebody else and does other things. And he said, in order to do the math, it's really, really tough when you have it's a burden on the customer to actually make sure they have all of the right distributions and all the right data for their case study. So to simplify it, we're assuming it's a constant failure rate. And at which point then we can just add the failure rates. It's very simple. And I'm like, okay, what are we giving up when you make it so simple that you get a nonsense answer out of it? It goes, yeah, that's true. But they're paying us for that, and they want MTBF, so we have to make it an MTBF value at the end of the day. But we add failure rates because it's simple. How is this in service to our industries? And it's like, well, we make money. Like, oh, bother.
Well, and it's especially frustrating because they do have that information, but it's just the MTBF or the fit rate that they're publishing.
Yeah.
Right.
Yeah. Well, you hope a lot of vendors have those things, and some don't. Some do, but they don't want to publish that. Some do. There's very small percentage that I've run across that actually give you decent time to failure distribution data. And they have test reports and data that support it. Whereas somebody making inductors, they have 18,000 models in their portfolio, and some they only sell 2 of. They're not going to run a life study for the sale of 2 of that particular model.
That's right.
So one of the things is that we want to know how well will this design work over time. What's its predicted failure rate over time? And there's all kinds of reasons we need to know that. Using a reliability prediction standard like 217 or all the variations of that has been a long, storied way that I've done that. In some cases early on, it was actually reasonable and it could be done. Yet all the barriers and hurdles and obstacles to getting good data out of that, not just failure rates, but just good data at all. And the capability we have today to do the math much better is also hampered because we just don't get the distribution data. So if you're working on something that's critically important, do the due diligence and create a block diagram model of it and get the failure rates, not just failure rates, but get the distributions and run that analysis out. We have great tools today that make that really simple to do. We don't need to just add failure rates because that's our computing power's limitations, which was originally why they used failure rates. So there's lots and lots of hurdles to this. If it's important, don't use prediction models. Mm-hmm. Do the real engineering to get good answers. If it's a condition of sale and nobody's ever going to use it in any meaningful way to make an important decision, other than it's a checkbox on the procurement form, yeah, crank it out and don't worry about it too much. But it's crazy that that's still out there.
Yeah, that they're still being published and sold and marketed for use.
Yeah. No, I figured after I'd stamped out MTBF, I'd go after prediction models. But slowly making progress on the MTBF one. So there might be a time when I create a website, no prediction models.
Maybe this episode will be the impetus for that.
That's right. Yeah. I shouldn't say prediction models because there are good ones. I'd say parts count prediction.
Right.
Yeah. That's what we're talking about. Now, interesting question. I'm sorry. It's not a simple answer to what do I think about them, because my short answer is never, ever use them. Ever. Long answer is more complicated than that.
And then, if a reliability engineer is working with a supplier, if they have a good relationship with that supplier, and maybe they would even need to create something in their contracts, like non-disclosure or something. Mm-hmm, mm-hmm. But you may be able to develop relationships with your suppliers in order to get the full information about the reliability of a component. Yeah. Have you had success with that too?
Oh, certainly. And sometimes it's, nobody ever asks us that. And it says, no, I don't want your fit rate. I want to know where that came from. I need a distribution. Well, very few, if anybody, ever asks us that. So we just give you the MTBF value, and then most people go away happy. Like, no, that makes me mad. So, and you gotta go talk to Sarah. Sarah does all that stuff, and she can explain it. And she gave me Weibull distribution data and all kinds of good stuff. Sometimes just asking for time to failure information, not a fit rate. Don't ask for a failure rate because they will give you a failure rate if you ask for it. Ask for what's the time to failure distribution and how do you know? What's the failure mechanism? Those kinds of questions get you better information from some people. Some vendors, well, here's the fit rate. That's the only thing we do. The other one is working closer with a vendor, and if it's a critical part, and saying, we need to know this time to failure distribution and what the failure mechanisms are. And they say, we don't know. We make components and we ship them out. And says, right, let's work together to create a test or do halt or do whatever to figure it out because it's important to us. And then we share that with them so that they can get better at doing reliability. So I've done it those two ways on occasion.
Yeah, partnering with the suppliers and the components for that kind of stuff is a good thing to do.
Yeah. But oftentimes, if you got 2,000 components on your board, you're not going to partner with the 60 vendors that are involved.
Yeah, or if you're producing something you're not going to be ordering a whole lot of stuff. There's more reluctance for that too. Like there's no promise of buying thousands of these components.
Right.
That can kind of sour a relationship too.
Well, that might be a subject for a whole nother podcast. There are things vendors need other than just sales. If they don't have the reliability information, but they know that it would help them in the market to have good, solid reliability and understanding of their components in these different environments, they may be willing to work with you to do that, even though you're only going to buy 20 components. The information is invaluable to them, and it gives them a quicker way to get to that expertise without having to do it themselves. So there are ways, even with very low volume situations, to partner with vendors.
Yeah, that's a good point to consider all the mutually beneficial ways of working together, what it can produce. Mm-hmm. Yeah, like you said, not just sales, but information they can use for other things for themselves.
That's right.
It's a good point.
Yeah. So anyway, it's an interesting topic, and so I'm hoping the listeners are like, okay, I'm going to do a side eye at reliability parts count predictions going forward. If you don't already have that, but Dianna, our listeners are brilliant people. They already know these MIL 17's not worth the paper it's on anymore.
Yes, but hearing the. I don't know. Like I said before, I liked hearing the background and the history of it and how things were developed. And that always gives me a better perspective of how to use something going forward.
Yep.
So I appreciate that, Fred. Thanks.
All right. You're very welcome. And, Dianne brought this question up, and it's maybe sparked a question in you as a listener. So head over to accendoreliability.com/go/SOR. You can find a couple of ways to get in touch with us there. The question I got last week was through LinkedIn. And so that's a way to get a hold of us, any of the hosts of the show. Plus, on our About pages, we have contact information there. So plenty of ways for you to get your questions or comments or ideas over to us. And we're just rounding the corner on over 800 episodes. So we're doing a higher proportion of episodes that are based on people's questions and comments to us. So we appreciate the input and keep it coming. We got many more episodes to go, and many of them are being fueled by customers' comments and questions. So listeners' comments and questions. So with that, Dianna, I think we'll wrap this one up and maybe address another question next time.
That sounds great. Thanks, Fred.
Thanks. Talk to you later. Bye-bye.
Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.